Welcome back to the course entitled Elementary Electrochemistry. In the previous class, we started learning about potentiometric titrations and we have discussed about the potentiometric precipitation titration. So, now in this class, we will discuss the potentiometric acid base titrations. So, in case of acid base titration, we generally need to have a hydrogen gas 1 atmosphere coupled with a platinum electrode and H plus of a known or unknown concentration C coupled with calomel electrode. So, in this case, the EMF of the cell will be E cell, which is equal to E hydrogen minus E calomel, or E hydrogen can be written as E0 hydrogen minus 0.0591 log of concentration of H plus minus E calomel at 25 degrees centigrade. So, E cell can then easily be written as E0 H2 minus E calomel minus 0.059 log of concentration of H plus. And now, what you know is that this E0 is 0. So, this is the minus E calomel, then I put a plus sign and you know that pH equal to minus log concentration of H plus, right. So, we can write it as equal to 0.059 into pH. So, using this equation, we have a variable pH. So, one can measure the corresponding pH, which essentially means E cell plus E calomel equal to 0.059 pH. So, one can measure the pH of a cell and continue a titration between acid and base and try to find out what happens to the value of pH when the neutralization takes place and the H plus ions are all consumed and you end up getting a solution of the base. So, in an acid base titration, H plus ions are consumed. As a result, pH continues to increase. And beyond neutralization, pH jumps close to 10 to 11, indicating basic solution. So, this experiment can be done by just measuring the pH of a solution using an electrode which can measure, which is meant to measure pH, which will be coupled to a calomel electrode, and this will give you the value of pH change with the addition of base. So, this acid base titrations can be of different types. Strong acid versus strong base. So, here I will take example of HCl versus NaOH. So, in case of a strong acid like HCl, when you take a solution of HCl, it is completely dissociated, and you will find that the pH of a completely dissociated HCl solution is something around 1 to 2. So, when we start the titration, I will demonstrate this experiment physically in the next class. You take a beaker and you take a solution of HCl in this and dip an electrode which will measure the pH of the solution. So, it goes to a pH meter. So, now the thing is, when you are trying to do this experiment, you need to keep in mind that NaOH, which is used to neutralize H plus, it is also a solution, and when you are adding NaOH solution to a solution of HCl, the overall volume of the reaction mixture is continuously increasing, and as you know, the concentration of H plus depends on two factors: number of H plus ions and the volume of solutions. So, while doing this titration, by reacting it with NaOH, we are continuously reducing the number of H plus ions. Reduction of number of H plus ions will result in reduction of H plus ion concentration. As a result, pH is going to increase. But while adding NaOH solution to HCl solution, we are also diluting the solution, which further will reduce the concentration of the solution, resulting in further increase in pH. So, there will be a problem of double decrease in concentration and double increase in pH, and it is not appropriate. That is why when this kind of titrations are done, if the concentration of HCl is in the range of suppose n by 100, then the concentration of NaOH is taken at least in the range of n by 10, if not n by 2. What does it mean? It means that we are taking very strong NaOH solution, so that it will require a very small amount of NaOH solution to neutralize that HCl solution. As a result, the overall increase in volume of the solution will be minimum. So, because of volume increase, the change in concentration will be negligibly small. So, the effect of volume increase on pH can be ignored. So, I will show when I do the reaction, we will use n by 10 100 about n by 100 HCl versus about n by 10 NaOH. So, you can easily understand that for 10 ml of this HCl solution, we will need about 1 ml of that NaOH solution for complete neutralization. So, now when somebody is measuring the pH of a solution with the added volume NaOH, So, when you have not added any NaOH solution, 0 volume of NaOH, suppose the pH is 1.45. Now, with slow increase in volume of NaOH, say 0.1 ml, for strong acid, what you will see that this HCl is fully dissociated. As a result, the pH will not change significantly. It may not even show any change initially. So, for about up to 0.5 to 0.6 ml, you may only see the pH is increasing from 1.45 to 1.55 or so, not more than that. Then slowly, when you are increasing to a neutralization point, suppose about 0.9 ml, you may end up seeing that it has gone to about 2.00, and then on further increase to about say 1.1 ml, you may see the pH has increased to 6.5. Suppose then it goes, you go to 1.3 ml, it goes to 7.8, and then at about say 1.5 ml, it goes to 9, and about 1.7 ml, it goes to 13. So, what you see is that initially there was no increase much, then the pH started jumping and it has gone to a very high value and reached 13. So, when you try to plot these readings in a graph paper, if we just plot pH in the y axis and volume of NaOH in the x axis, you will see that the numbers are falling on a straight line in the beginning, and then towards the neutralization it increases. Over a period of 3 or 4 or 5 reading, it increases and goes, and then again gets stabilized, and it gets stabilized say around about 12. So, this will be the nature of a potentiometric titration curve for strong acid versus strong base. So, now like the previous experiment where we were talking about delta E versus delta V, here you can plot delta pH versus volume of NaOH. So, what you will see is again interesting. If you plot delta pH versus VNaOH, you will see that initially there is no increase. It may be flat, it may be very close to 0 or 0.01 or 0.02, something like that, and then near the equivalence point it will show a peak, it will come down, and then again there will be no difference. So, wherever it reaches a peak, that volume of NaOH is your neutralization point. So, using this method, then one can easily determine the concentration of unknown solution of HCl using a strong base NaOH without using any indicator. What will happen if you use a weak acid with a strong base? So, suppose weak acid is acetic acid and strong base is NaOH. So, as you know, this weak acid is dissociated as CH3 COO minus plus H plus, and this dissociation is very feeble in any aqueous medium, and most of the time acetic acid stays as undissociated acid. So, if you do the same experiment using acetic acid in place of HCl, you are going to see something different. You need to take the reading in the same way as I discussed a little while ago. and you will then plot this pH versus volume of NaOH. Now, in this case what will happen? In this case, when you have H plus ions very little, the concentration of H plus ion is less. So, at the beginning at 0 volume of NaOH, pH will be little more than the strong acid, it will be around 3.7, 3.8 or something, 3.7 to 3.8. And when you continue to add this add NaOH dropwise, you will see that it is no longer as flat as it was for strong acid. The pH is continuously increasing, but then near the equivalence point it increases sharp, and then the rest of it follows like your strong acid, strong base, it goes to about 12 to 13, right. So, now when we have this plot and we have the entire data, we will then plot delta pH versus volume of NaOH, and you will see that here the plot is slightly in the increasing order. Then the peak appears over a bigger, wider range, and then it increases like this. So, again this tip will indicate your neutralization point. Suppose the tip indicates that this is the neutralization point at this point where you have the maximum jump. So, this is your neutralization point. So, this volume. So, now we have not yet discussed the method of Henderson equation. So, using Henderson equation, one can determine or calculate, one can determine the pKa of this weak acid, and as per Henderson's equation, the pH of a solution at half neutralization point, suppose this is x ml. So, at x by 2 ml, whatever the pH, it corresponds to the pKa of acetic acid, right. So, one can determine the pKa of a weak acid using a potentiometric titration. You find out the end point, find out what is the half neutralization point, and then from the graph paper you can find out what is the pH at that half neutralization point. So, that will give you the pKa of the weak acid. So, we have discussed about strong acid, strong base, weak acid, strong base, and we will now talk about a third possibility of weak dibasic acid versus strong base. So, weak dibasic acid is oxalic acid versus NaOH. So, now COOH, this is oxalic acid, dissociates in two steps, COO minus, COOH, and then in the second step COO minus, COO minus. So, here it is plus H plus, and again here plus another H plus, right. So, it has two steps. As a result, it has pKa 1 and pKa 2, right. So, now if we try to do this experiment as usual, as I have described in the previous case with weak acid, strong base, what will happen? When I try to plot pH versus volume of NaOH, again it will start around 2.8 to 2.9 kind of pH, and slowly you will see there is an increase in the pH. When it reaches the neutralization of the first part, the first acid, it will increase little, and then it will again slowly increase till the second H plus is getting neutralized, and at that point when the second H plus is neutralized, you will get to see that it forms a solution of NaOH, which is pH of 12 to 13. So, now if we plot this experiment in terms of delta pH versus volume of NaOH, you will see that initially it was increasing. You have a small peak like that, again it increases very little, and then a tall peak and it goes. So, this first point is V1, first neutralization. This second point is your second neutralization. So, that is the point where the first acid is neutralized, and this is the point when the second acid is neutralized. So, suppose this is the value for V1. So, this point, which is V1 by 2, the corresponding pH is your pKa1, and then this volume V2. So, middle point between V1 and V2 is somewhere here. So, that it is basically V2 minus V1 by 2. The corresponding pH that we get is the pKa2. So, using this experiment, one can determine the pKa1 and pKa2 of oxalic acid if you do the experiment very carefully, and also one can of course get the equivalence point or neutralization point. So, one can estimate the concentration of oxalic acid solution using NaOH, or in the reverse way one can do a standardization of NaOH using a standard solution of oxalic acid. So, with this I will stop in this class, and in the next class, in the next week, we will demonstrate these experiments which I have discussed in today's and the previous class. Thank you.